like in active region shown in different wavelength observed from SDO. So you can see that active region which is flared shows intense brightening which can last from for few minutes, and these are very highly energetic events that can be observed especially in UV and X-rays. So this is one of the signatures. So currently I will just tell you some signatures which are generally associated with CME. So like some ejecta, like in this previous example, which is going out from the corona, or some flares, or in other cases there are prominence eruptions, like in this particular movie. You can see this dark red features in the left side as well as on the right side. When these features get unstable, uh, they are erupted outwards and they form the CME. Or in some other cases, apart from these kind of eruptions, there can be some post flare loops. So the example which I am showing here, there are already some existing magnetic loops. There was a flare ejection, and you can see that there are some new loops which have emerged after the eruption. So these are called the post flare loops. So this is the flaring region, and these are some of the new loops which have come apart from the existing loops. So this is one of the signatures that which we have seen over past many decades whenever there is an eruption, and some post flare loops have been identified because of the reconfiguration of the magnetic field. The next signature, okay, this same event, if you just see the step-by-step snapshot in the time series, you can see that after the flare has taken, these new loops have formed, which last for several minutes to few hours of the time. And another interesting feature which one can observe during CME eruption is called the coronal dimming. So if you see the sequence of images after the flare, there was some eruption, and you can see that there is all of a sudden a dark region which has appeared. Initially, there was not so much of darkening as compared to the previous figures, if you see, or in the bottom panel also you can see that in the difference images, this is actually prominent. So people believe that earlier it was used to believe that it may be because of the change in temperature in this region that they appear darker, but it was found that in fact the coronal material itself get discharged, and hence because of the low density in these regions they get dim, and this feature coronal dimming came into existence, and these are also associated with regular kind of CMEs. Or in some other features, if we notice here the same event, there was a very big eruption, and then you can see the wavefronts propagating throughout the corona. So these are called the UV waves. So if there is a very big uh, coronal mass ejections, then you can see such kind of waves propagating throughout the surface of the sun as well as in the coronal heights. So these are some of the prominent features which we observe during typical CME, especially the ones which I am showing like UV waves or flares. These are like kind of extreme for extreme CMEs, like very fast CMEs with speed, say going up to 1,000 km per second. But one or the other features can be identified like coronal dimming or prominence eruption or some erupting material that you can uh, identify from the disk itself. But uh, in case of stealth CMEs, this kind of any of these signatures will not be present. So I'll just go back to the paper here. So these people, they mentioned the stealth CMEs. So as the definition goes, that none of these kind of signatures, which I just showed you till now, will be visible for stealth CMEs. So what is the implications? Because in case if a CME is originating on the surface of the sun and it is directed towards Earth, and you are unaware, because what happens in the coronagraph images, you have blocked the solar disk, and if a very faint CME which do not have any disk signature comes towards us, you have no idea that a CME is approaching you. So that's where the identification and study of stealth CMEs based on like how to uh, identify them based on some form of image processing or other becomes very important. So this part I have already told you, the different eruptive signatures. But there is one more thing, like just now I mentioned about the CMEs which are directed towards Earth, which are popularly called as hello CMEs. So in the catalogs of the CMEs, so they are there are CMEs which are termed as the backside CMEs. So if you see their movies, like in here, so already there are some flows, and you can see that there is a CME which is directed either towards you or away from you, but you cannot save just from this particular movie because the disk is blocked. And if it is a stealth CME, you won't be having any signatures on the disk. So you may assume that it is going behind the disk. That can be possible because it's in the difference images. You don't have any information about that. So if I just play this movie again, you can see that the this eruption, which is like concentric circle moving outward. So what if it comes towards us and we have identified as backside CME? So like in the catalog, we have called it as a backside. So there are n number of CMEs which has been cataloged as backside, but maybe these can be stealth CMEs also. So that's where the study of these kinds of CME becomes important to understand how they have originated. So generally there is speed means there have been few statistical study which have revealed that they have speed less than 500 kilometer per second. So if you draw the spectrum of the speed distribution of the CMEs, so these typically lie in the lower end of this kind of distribution, speed ranging from few kilometer per second to at max 500 kilometer per second. But even that the kind of speed is sufficient for causing disturbances on Earth. So people in the past have raised some fundamental questions, like whether these are really stealth CMEs or it is limited because of our observations, because of our resolution, or because of our image processing. So these are some kind of the questions which have not been solved fully, and these people, these authors have tried to address some of these particular observational questions. So there are some models for the typical CMEs, like breakout model and kink or torus instability. So there is a review article if someone is interested for this different models of CME eruption. So they can go in this with this particular Green et al. 2018. So yeah, so it is also seen that most of the eruptions happen lower in the corona, but these authors, James et al. 2017 and 18, have proposed a model that these kind of eruptions can occur higher up in the corona. So this is typical one theory that can that suggests that because it is happening higher up in the corona, it may be not so evident in the disk images which we generally see. So generally, the CMEs have means the kinematic profile have three phase. The first is a slow rise phase, which is around the average speed is around 10 kilometer per second. And then the second is the accelerating phase, where the speed abruptly increases to even up to 1,000 kilometer per second. And this is where the main energy is released, like the magnetic reconnection or the flare is happening. And once this process is achieved, then it is launched, and which is propagated in heliosphere, and it reaches more or less the solar wind speed. So this is the scenario of a normal CMEs. But do the stealth CMEs also um, follow this kind of thing? So there is one example for this particular part which I have highlighted here in this particular study. So I
Hello,
will, yeah,
Ritesh.
yeah,
Yeah,
yeah.
this is Rakesh. So I
Ha,
have a
Rakesh.
question regarding this
Mhm,
scenario of three phases.
mhm,
So you have told, if I correctly understood, that this accelerating phase you connected with the reconnection,
mhm,
but this when it gets slow rise, but
mhm.
when CME initiated got erupted, then itself the reconnection happens. I had some kind of idea like that. And when you are talking about this acceleration phase and then reconnection, then exactly between which like magnetic field lines it reconnected with. So can you little bit elaborate on that?
So see this
Uh,
the three phase which these authors Zhang et al. And these people. So they have theorized based on few statistics which they
right,
have observed. So
right.
initially, when we are talking about the slow rise phase, the
Uh-huh.
flux slope is just rising in the corona. It's
Okay.
still not unstable. So like when
Uh-huh.
there is kind
Ach-
of reconnection at the foot points, then
uh-huh.
abruptly the speed is increasing. So the
Uh,
slow rise, the flux slope has just emerged outer in the corona, and it may be still persisting like the prominences, it may be still
Still,
persisting for
yeah, right,
few days
right,
or something
right,
like that. And
right.
so that's the slow rise phase. But
Uh-huh.
when this reconnection or flare happens, so or any kind of other
Uh-huh.
instability like kink or
Right,
torus,
right,
so
right.
all of a sudden that flux rope is ejected or thrown out
Uh-huh.
in the
True.
heliosphere.
Yeah,
Yeah.
yeah, clear. Okay,
Yeah.
thank you. Go ahead.
Okay.
Yeah.
Okay. Yeah. So, okay. So these are all that So there's again one debate between among the community, like what to call stealth CMEs. So some people believe that the stealth CMEs do not have any coronal signatures at all, but other people they feel that there can be some weak or low coronal signatures which are we are unable to identify. But in both cases, the this kind of CMEs are equally dangerous if we fail to identify before they impact our earth. So I'll go to their particular study about what observations and methods they have used. So this is the list of the instrument which they have again produced in the tabular format, different instruments, UV imagers, EIT, UVI, and AIA SDO. And apart from that, they have magnetograms of MDI and HMI, and white light imagers, the coronagraphs of LASCO and stereo. So they have used these data sets for two particular cases of stealth CMEs of 27th October 2009 and 3rd March 2011. So they have also mentioned the wavelengths of the UV which they have used along with the other properties. So in these images, they have used something called graduated cylindrical shell model and stack plots. So the stack plots is basically for a particular location. So I'll just show you example about a stack plot. So at this particular angle, they have stacked with time all the heights. So if you just stack with time, you will get something on the right. So on the top panel is the outer corona, which is seen by Corwin, and the bottom, the inner one is represented in the bottom panel. So all along this particular black line, which is shown in this first figure. And yeah, we'll talk about this in few minutes. So they have also mentioned here that they have used multi-scale Gaussian normalization technique in UV images. So this technique actually enhances the features which are very, very faint or low in contrast. So just to show you an example, in this particular figure, which is taken in AIA 171 angstrom, you can see there are very distinct contrast features, some bright features here, some very, very dark features, and even the these loop structures are very much kind of diffused. But if you apply the MGN technique, multi-scale Gaussian normalization, you get something like this. So you can see that the bright features as well as the dark features all come in a kind of same footing, so that you can identify all the features at the one go in a single image. And on the top of this, these fine structures, the loop-like kind of structures, or this oval-like prominence, all these fine structures are also getting enhanced with the help of this particular technique. So any kind of minute details can be observed clearly after enhancing. So these people have applied similar this technique in the UV data sets which they have used. And then there is GCS model. So what is GCS model? So based on the multiple viewpoints. So if a CME is directed, say here in this direction, it is being observed by this spacecraft, A spacecraft, and there is LASCO also. So these A and B represents the location of stereo ahead and stereo behind, and the LASCO spacecraft will be in the Sun Earth line. So based on the observation of the same CME from different vantage point, there is this GCS modeling. Yeah, so you fit a kind of model to the observed CME from different vantage point. Like the black one here representing that. shell of the GCS model, which is simultaneously fitted in the core to A as well as core to B. So at the near simultaneous, so this for this particular example, 9th October 2000, okay, sorry, 27th October 2009, at this near simultaneous time, they have fitted the GCS flux rope. It is kind of visual fitting technique which they have used. So yeah, going back to the GCS modeling, so yeah, so that was used uh, so as to locate or localize the foot points where the CME can be, because as I have told earlier, that stealth CMEs may not have a very distinct on-disk features. So using the GCMS model by fitting the CME, which is well observed in the outer imagers, so they try to localize the foot points so the source region can be identified. So this is just for localizing. And and okay, and then further they have talked about the stack plots. And yeah, since there was no obvious signatures, so they have tried running difference of different time intervals. Like for some cases, they have, I guess, 30 minutes difference. So these 5, 10, and 30 are actually the temporal pass bands of this particular imager. And similarly for AIA, they have used 2, 5, and 10 minutes of separation. And here they have mentioned what was the separation between the different spacecraft. So that is shown in this particular figure, that how much A and B were away from each other when this particular CME of October 2009 was observed. And in this particular case of March 2011, these A and B were like around 180-degree apart. So yeah. And yeah, so there are again they have discussed about some other technique like wavelet based techniques and noise adaptive fuzzy equalization techniques to enhance the UV images. But MGN technique being computationally effective, the one which I showed you the example, this example, and easy to apply. So that's why they went for this particular technique to enhance the UV images. And they have also used a technique called running ratio for image with 3 hours of separation in UV images, so as to identify if there is any dimmings which is associated with these CMEs which they have studied. And they have also used the magnetogram, MDI and HMI, to understand the evolution of the surface magnetic field of which can be associated with these two eruptions. So this was just a description of what all tools and techniques they have used for studying these CMEs. And yeah, there was one radio observation also by 9K radio heliograph. And yeah, they this is some cleaning technique for their radio data. And moving on to the results, so overall they have mostly looked into first these kind of stack plots. So as I told earlier, that along this particular angle, they have generated the stack plot. So when the CME was erupting, you can see that there is a bright ridge which is present here. So you can see that the shape of the ridge. So as Rakesh was pointing out, the slow rise and the fast acceleration phase. So here it is evident that this is kind of an exponential kind of curve. So initially that this part, the lower part, is very slowly, it has increased in height from 1.5 to even less than 2 in from this particular time, 16 of 16 to around, I guess, 12 of this particular date. And all of a sudden this shape has changed, so like kind of exponential. So these people have tried to fit this ridge with the exponential fitting as well as the parabolic fitting. But you can see that exponential is better fitted to this particular eruption rather than the parabolic one. So based on the theoretical modeling and simulation, it has turned out that this exponential fit uh, occurs whenever the instability is a kind of torus or king stability, whereas the parabolic fit or the quadratic fit is there whenever there is a breakout model scenario. So these are the different models for CME eruption, and based on just the kinematic profile, one can uh, tell that what kind of instability will be leading to this kind of eruption. So since it is concluded that the exponential one fits better, so they have suggested that maybe this first it belongs to the first category, and there will be either torus or kink instability. But because we do not have any observation about uh, their source location, so it's difficult to say which is actually present. And yeah, since the main aim was to look in the lower height signature of these kind of eruptions, uh, the stack plot for the UV images, the lower boundary is also plotted here. So you can see that for the same time, when the CME has reached the accelerating phase, the sudden rise phase, there was a kind of brightening in the UV images. Till here, there was nothing, but all of a sudden, near the similar time period when it has started accelerating, there was a brightening which is observed here. So these authors suggest that it may be related to this acceleration phase and may be providing sufficient energy to this eruption to accelerate outwards. So this is evident directly from the correlating these two plots. And there is again as you can see, that distinct concave up kind of shape, and which they have used in the I guess this fitting using the GCS and trying to localize the foot points and this two locations. So they just in the text they have overall they have from here to in the analysis part they have uh, talked about these two plots and the relation between these acceleration and the UV brightening. And apart from that, they have also looked at the different uh, activities that were going on prior to this particular eruption. So somewhere they have to mentioned. Yeah, there was one more eruption one day before this particular when this particular stealth CME was observed. Okay, it might be somewhere. Yeah, in the table, it's there again at the last. So one more thing. So uh, in the Core 1 and Core 1A and Core 1B, these particular eruption was identified at different times. So implying that it was near the limb of one particular instrument as compared to the other observation. So yeah, so using the MGN technique in the UV images, they try to correlate the brightening which they have identified here, the fitting which they have done here, and locate the source region. So before the eruption, so the event which we are talking here is of 27th October 2009. But uh, before that particular eruption, as I mentioned, that there was one eruption on 26th of October, and this particular active region, along with the other one, which showed some kind of flows. So these people were trying to figure it out if this first eruption is responsible for opening up the field lines, and so that some even the small eruption is turning out as a stealth CME. So it is very tricky task to identify the source region when you do not have any clear distinct evidence. So based on the MGN filtering and the foot points of the graduated cylindrical shell, this model, they try to locate on the magnetogram and the UV. So here the blue crosses represents the foot points from this model, this GCS model after fitting the CME. And the red point is the location of this source region determined by a previous study for the same event. So you can see that these are more or less close to each other, but still there is no active region or any polarity inversion line which is clearly evident either from the magnetogram or from the UV imager. Though there is one active region located in the like top right side, which is both visible in magnetogram as well as in the UV imagers. But there can be possibility of deflection, obviously, but from this time for the time being, uh, we do not know actually if this particular active region is responsible for generating this stealth CME, which may have deflected and giving the coordinates to this particular lower location. So that's ambiguous to just conclude that if this is the location or this is the location. So for this thing, yeah, so mm, that is kind of thing, because there was one small active region which was emerging, and apart from this they have also observed that several bipoles were emerging and coalescing, and maybe it's not the flux cancellation but flux emergence which is responsible for this particular eruption. And similar kind of analysis they have done for another event of 3rd March 2011. Again they have tried to localize the foot points. Here again, the blue one from the modeling, as shown here, by just fitting the GCS model and trying to find out the location, and red one again from one previous study. So here again, you can see that there is one active region which is located in between all the speculated source regions for this particular event. And moreover, if you just plot the stack plot here for this TME in this direction, again, you can see that there is one ridge. But here they try to fit the exponential as well as quadratic, but none of them proved to be better than the other. So it's looking more or less like both are overlapping. And as for the previous case, there was some enhancement in UV. Here they did not find any kind of enhanced structure or something when this CME has started to rise. So this is kind of the eruption mechanism is could not be directly told, like for the previous one based on the exponential fitting they told that some instability is there, but for this case no such clear demarcation is there. You can say from model that okay, this particular CME has origin by this instability or breakout thing. So this was the uh, ambiguous part for this particular CME. And the source region, again, so it can be believed that this particular location may be responsible. But if you just recollect the location of the stereo spacecrafts for this particular event, they are located like 180-degree away from apart from each other, and the CME is more or less towards the Earth. The second event, the second one, 11th March, 3rd March 2011. So when the CME is towards the Earth, with no distinct signatures in the disk, like we were discussing in the beginning, that if you do not have distinct signature and if it is directed towards the Earth, so this is one case. So just notice here that for stereo B and stereo A, the CME will be on the limb, but for the sun earth line, it will be halo. So B is looking in this direction, A is looking in this direction. So and CME is propagating towards earth. So since these are the limb events for A and B, so the signatures, there are three viewpoints. So for B and A, the signatures will be in the limb side, but from the Earth perspective, it will be on the disk. So that's what the authors try to use, take advantage of the three vantage point, and they have shown here uh, from the the UV images from stereo A. So UVI A is onboard stereo A. So here you can see that there was some structure which happened to like kind of untangle or something like that. Means some activity was going on. So this was on the limb for stereo image, but and this correspond to this particular location for the disk image. So you can see that because the CME may be associated with some twisting of this particular shape. So and apart from this, the twisting, they also observed some dimming. So they took the running ratio image of the AIA images, and this is the location where they found that the UV intensity has reduced, this one location and this location. And one thing to notice here that like in general, we just take 1 minute or 2 minutes of running difference or running ratio. But for this, I guess it was 30 minutes difference when this significant observation could be made that there is some uh, dimming which was actually the signature of CME, but because of the very slow rise or very faint signature, it was not evident in just 1 or 2 minutes. So any questions till now? Yeah, okay, I will proceed then. Okay, so this was about trying to localize the signature. So if you combine this image and the another image, the foot points which they have obtained, and overlap in a plain image, you will see that the dimming locations are very close to the locations which are identified with the foot points of the CME by modeling. So foot points are obtained, just to remind, by this method. So all these locations are like very narrow region of I guess 200 by 200 arc second region, and the distance is not much from the location of dimming which has been identified. So this particular active region, they have tried to link it to the stealth CMEs, because now you have again seen the dimming signature here, and the foot points are also located here, and some motion you have seen in the disk image from the stereo images. So apart from this, there were some flows also and some very faint loop-like structures which originated. So all these point out to the fact that maybe this particular active region was associated with the stealth CME of this thing. And they since they had uh, this data, what you call radio data also, so using the density model, so there is a standard Newkirk density model at 150 megahertz. They tried to find the height at which some radio emission had been observed. So this, for this particular event, the second event, they had observed at 150 megahertz some emission. So they tried to localize, and it turns out it is also in the near vicinity of that particular active region. And moreover, the height at which this emission was observed was around 1.34 solar radii, or should I say, 0.34 solar radii above the surface of the sun. So, since there was not much emission in higher wavelengths, so they concluded that the acceleration of the electrons may have occurred at higher heights, and hence this also supports the fact that um, uh, the that instability might have happened at higher heights, and CME has started rising at like say 1.3 or close more than that height. So that's why you do not see much of the disk features, because at this particular height already the density of the corona has reduced very much. So even if there had been a very faint signature, it would have been very, very much difficult to observe directly with the conventional image processing techniques. So this was the height was determined by this method for this particular uh, eruption. So based on these two particular event study, so both have some signatures linked to the active region, and yeah, the height of occurrence may be higher than the usual coronal, lower coronal heights. So that's why we are unable to say it. So in the discussion part, they have told the implications of these kind of studies. So any question till now on the methodology? Okay, I presume that it's clear till now. Yeah. Okay.
But Ritesh, I have a
Yeah.
question.
Yeah.
Probably it
Yeah.
is quite very naive question. You said some back CMEs are could be misclassified as these, right?
No, ma'am. It can be reversed. Like the stealth CMEs can be misclassified as backside CMEs.
Oh, okay, the other way around.
Yeah,
Okay.
yeah.
So
Because we
now
do.
you're saying,
Yeah.
yeah. So now you're saying that this may be originating at a higher height, right, of the corona.
Yes. Yes. Yes.
So does that tally now, or doesn't tally?
Actually, like before the launch of this stereo spacecraft. So currently, if I go back to the location plot, So since these are constantly orbiting away from Earth, and we can have multiple vantage points. So suppose if is looking here, so more or less the complete sun is visible to us now. So if even if there is signature on the backside of the sun, it can be covered by A and B from different directions. But when these spacecrafts were not there, just we had sun earth line observation, during those times, uh, if there is a stealth CMEs which is earth directed, but in the coronagraph images, since the stealth CMEs do not have any on disk features or on disk phenomena like associated flare or anything, so those were regarded as backside CMEs. So we still do not know so whether those are really backside CMEs or maybe stealth CMEs which did not have signatures. So until these stereo spacecraft, we did not have information. But still, with the use of stereo spacecraft, is still difficult to identify the exact location, what is causing these kind of CMEs. So the higher height conclusion which we have come now, maybe because at higher heights the coronal density is also very less, so there won't be much of emission, and even the magnetic field is very weak as compared to the photosphere or the lower coronal heights. So that kind of flare or intense brightening are not evident for those higher heights. So, but again, stereo B is dead now, and we are only left with stereo A at present. So maybe we may need one more vantage point in future. So yeah, so we do not know whether it is back or not at present, but maybe a long list of such backside CMEs could be stealth CMEs, but a separate study can be done to just for the backside kind of events with the stereo era.
Okay, thanks.
Yeah. So moving to the discussion part. So why this work was important? So previously, these stealth CMEs were associated with the open magnetic field or the quiet sun, because these quiet sun are believed to have a weaker magnetic field as compared to active region, or even the open magnetic field, like the CME can easily propagate without showing any signatures. But this kind of study which these authors have done, incorporating some image processing techniques, so they have shown that it may be possible that it is associated with active regions, but since they are originating higher up in the corona, so we do not have that kind of signatures, on disk signatures. So that can be one possibility, which is again in support of one previous study by Alzate and Morgan. Another thing, like current models which are mostly related to the lower corona, so maybe we need to revisit what if the instability happens higher up in that kind of atmosphere. Because for these kind of CMEs which they have studied, there was no, not very much a stronger active region. But one more thing which they noticed, that the polarity inversion lines, the region between the positive and negative polarity of the active region also was very small as compared to responsible for the large eruptions. And moreover, these polarity inversion lines, so if I just go back to the magnetic field information, so you can see the polarity inversion line will be located somewhere around here between the positive and the negative polarity. And generally, for a CME to happen, any kind of shear is required, so that there will be some tilt in the polarity inversion line because of the differential rotation of the sun. But since you can see it's more or less like parallel to the axis of the rotation of the sun, so they are pointing out that maybe the differential rotation has not still acted on these kind of eruption, and that shear theory which we have for the eruption of CMEs is not much valid for this kind of stealth CMEs, because you can see that there is not much tilt or any tilt of the polarity inversion line. So maybe the flux emergence is responsible rather than flux cancellation for such stealth CMEs. And yeah, and there was one clear concave up structure for both these kind of CMEs. Another thing, yeah, another thing which I had talked just now about a high altitude eruption of this kind of CME, because the density as well as the magnetic field is very weak as compared to the photosphere or a lower corona. So that's why those intense flaring locations could not be seen for this CME, for these kind of CME. Uh, okay, I guess there is some more points. Uh, okay, yeah, I guess they are again talking about the active region. So yeah, they have also looked into the gauss X-ray flux. So so this is a near Earth observation of the X-ray flux. So you can see that this during the complete profile of this the two eruptions, there wasn't much change in the X-ray intensity. So if you see that minimum the C class flares which we talk about for most of the CME, so there wasn't much of activity going on which could be associated with the flaring kind of active region for both the cases. So yeah, these are some of the signatures which they try to identify with all the available data sets. So here they have pointed out uh, that the shearing part which I had talked about, because there was the polarity inversion lines appeared more or less parallel to the axis of rotation, so the shearing might not be responsible for the eruption. So generally, like first question which Rakesh da asked about the slow rise and other things. So generally, this flux rope which is associated with CME are comes from the lower corona and then they erupt. But uh, based on this case study, so there is a question which they have put forward, like maybe the flux rope is forming at a higher altitude and then it's reconnecting. So this is kind of challenging to our current modeling of the CME. So yeah, so that's I guess for modelers this paper is presenting a new challenge. And moreover, so they have also emphasized on the possibility of what the instruments sensitivity and resolution plays a role, because just by looking at the normal images, uh, it's very difficult to identify the locations. Maybe by combining different image processing techniques or extending the field of view of our full disk images. So like currently the UV images which I have showed till now, AIA has field of view up to 1.3 solar radii, UVI has up to 1.6. But even after having 1.6 solar radii field of view, the the source is believed to be higher than those particular heights. So this is emphasizing the need for future UV imagers which can cover to larger distances. So this is again they have put forward, like from for the instrumentation part, like the future missions should have these kind of imagers which can look farther in the corona in the UV channels, so that actual reconnection mechanism or the origin of these kind of CMEs and how they are different from the regular CMEs, those can be addressed. And maybe perhaps then we have a better understanding about this CME kinematics and origin. So I guess that was the paper. Yeah, that's the end. You can have a questions.
So, so
Yeah.
this is Rajaguru here. So
Yes,
these
sir.
two stealth CMEs had did they produce any geoeffective disturbance? Any were they geoeffective?
One of them, sir. So the second one is Earth directed, and it was geoeffective. But the first one did not was away from the Earth direction. So the second, if I just show, so this is towards Earth, and it was not so much because it was like kind of leaving the equator our plane. But yeah, so it was Earth directed and had some effect. But the first one was directed away. So yeah, the second one was in this direction, Sun Earth line.
So it looks like the conclusion of this paper is that these are not very different phenomena. It's just a low energy, low end of the spectrum of the CME energies and
Yes,
other.
sir. Yes, sir. Yeah, that's what they want to emphasize, that only because of our limitation of observations, they are treated as different.
So right, right. In that case, a majority of them will not be geoeffective because they are anyways low energy, isn't it?
but they still contains the magnetic field and some plasma density. That's why they could be still identified in white light images.
Okay, so do we know enough statistics of this? How many of them are like in as a function of cycle over solar cycle? What percentage are stealth CMEs?
So currently, these people at MSSL and all, they are preparing a catalog with the EC committee and all. So means the exact numbers we do not have, but some statistical study they have done. I guess there was one review article by Lucy Green or Howard. So there they have talked about, I guess, solar cycle 23. Yeah, this article. So I just had a brief overview, but means not much idea about these particular phenomena. But yeah, these people are believing the in this review also they have emphasized that maybe it's just like a lower energy end of the CMEs.
Okay. Okay.
Okay.
Thank you.
Yeah.
I'm just, I mean, curiously, it's a curiosity question. Why do you call them stealth?
Uh, Ma'am, because these
Because it's completely not known or something like that. It's
No, no, no. These appear in the coronagraph images, in white light images, but they do not have the signatures, the general signatures which I just showed in the presentation. So, like neither any X-ray flare or any kind of prominence eruption or any wave associated or any loop post flare loop. So, since there are not much evidence like where these are originating from, so that's why they were termed as stealth CMEs.
okay. And regarding strength, maybe you said it, but I haven't been able to catch it.
Mhm.
But how are these with respect to the normal CME? What are the energetics like?
So, yeah, yeah. So these like the normal CMEs can have speed up to 1,000 to even 2,000, 3,000 kilometer per second, means the extreme ones, where the average one may lie up to in the range of 400, 500. But majority of these stealth CMEs, based on some statistics, have speed less than 500 kilometer per second. So that's why they are regarded to be, means the energy input to these CMEs may be lower than the typical CMEs which we see normally.
Okay.
Okay.
So Ritesh,
Yeah.
are they stealth just because they are of less intensity, or there's any other reason beyond why they are stealth?
Only based on from their origin perspective. So if we do not see anything on the disk where they are originating, so they have been regarded as stealth. But other characteristics like kinematics and other also in coronagraph, they may appear as faint structures. So yeah, but nothing so much different from the normal structured CMEs.
Okay.
Okay.
Do you see any of the radio signatures for these?
Uh, for one of these CMEs, so in these two case studies, so they tried to look for one radio heliograph. So the second event, they found some emission in near 150 megahertz, and when they try to localize, they found
Okay.
the location will come somewhere
Yeah.
around here.
Okay.
Yeah, but again, like in the normal CMEs, there will be a band of spectrum which could be seen in radio wavelengths, but here only few wavelengths was visible.
Okay.
Ritesh,
Huh.
yeah, Priya. So, are there any other flaring phenomena like
Mm-hmm.
which can be confused as this stealth CMEs?
No, actually, they are two different things. Like the flaring thing, which we generally see, means which we have understood till now.
Huh.
So, usme means the energy output goes. Yeah, okay, I will show you this plot. So the minimum which we can detect is like 10 power minus 7 watts per meter square in X-ray.
Okay.
So though the signature is above this, but continuously on sun, these kind of means this low energy flaring happens. So if the flare is responsible for the CME, this kind of, so it will be difficult to separate from the background intensity which is already being recorded by our spacecrafts. So these are
Okay.
like kind of the floor level flare intensity.
But Ritesh, this
Yeah.
10 power minus 7 is the GOES limit, right?
Yes, yes, yes.
But like, I mean, we have other X-ray, like, no, maybe the Chandrayaan 2 also has this
Yes,
X-ray,
yes, yes.
which can go even below
Uh,
it.
yeah, so in the
So
recent, I guess one presentation, the Chandrayaan people showed the results.
yeah, yes, yes,
Yeah.
yes.
So
Z-
there, their floor is even below the GOES floor. But again, it will be interesting to look into their disk counterparts, because again, the disk imager will have its own limitation with respect to the sensitivity. And
Yes.
if you remember the recent campfire video of solar orbiter, there can be like n number of small flares that are continuously happening. So those may also contribute to the X-ray flux, which we may get confused with the stealth CME flux.
Okay.
Okay.
Yeah.
Okay. Okay. Thanks, Ritesh.
Okay.
So yeah, Ritesh, so I was also wondering whether there is any special uh, property on the so on which from which part of the sun they are getting released. Is there any dependence for this kind of CMEs?
No. Actually, it can happen anywhere. Only thing is, uh, because of this, because in general case, the for normal CMEs, because the on-disk features are so bright, we can localize them. Like, okay, it is happening on the disk or the in the limb. But for these kind of CMEs, since we do not see any eruption or something from the disk, so it's difficult to localize. But they may follow the general trend of normal CMEs. It can happen anywhere, kind of thing. But for this particular case study, which they have taken from active region, so since the active region belt is plus minus 45 degree close to that, so if it is associated with active region, so it will be within this band of latitudes.
Okay, thanks.
So the one of the this one of these two analysis two stealth CMEs analyzed were observed by stereo at the high
Mhm.
altitude, right? That's what you said.
Means high altitude was the origin which they speculate at around 1.3 from the radio data they got it using this density model, Newkirk density model.
Oh, it was not seen in stereo.
Uh,
It was
stereo
it was
radio.
on disk. Is it?
This was for the second one was on the limb for stereo. So yeah, so for this second event, they witnessed this kind of some like twisting of magnetic field just before the eruption, few hours before the eruption. So this, if
Okay.
you relate it with the coronagraph image, so this something it goes like this. So this twisting was related to the this bubble which is expanding outwards.
So could they identify a model to explain this? Is it
Yeah,
a reconnection or something else?
recently this group have developed some model extrapolation technique in which they are using higher heights, means pfss they have extended and doing some something, means I am not so much aware, but I have seen just the presentation of one of these girls.
Okay, but
Yeah.
they okay. So these people also conclude that it's a high altitude, some kind of a reconnection due to something else happening, a newly emerging flux.
Yeah. So that can be like one thing, as you pointed out. So since normally what we see the reconnection happening very near to the surface of the sun, but for this kind of thing, maybe it is beyond the field of view of these images which we have. So that's why we are not seeing it clearly.
Okay.
Yeah. So that's why these are also emphasizing that the future UV imagers may have extended field of view, so that such phenomena could be observationally verified.
Okay.
Okay, I guess Shairi.
Yeah, so is there any other question? Okay, if not, then let us thanks Ritesh. So it was a very nice talk.
Thank you.
Thank you,
Thank
Ritesh.
you.
Thank you, and
Ritesh.
Yeah. Thank you. Bye.
bye.
So I just wanted to announce something. Um, so we have the feedback form will be available, and so we can fix a date till which we can give feedback. So until the next journal club, this feedback form will be available for giving feedbacks to students. So please give feedbacks because they are very important, and your constructive comments will also help us in improving our presentation and our anything you want to point out. Anything will be good. Okay.
Where is it available? Where will it be available?
Oh, it's in the mail itself.
Okay, okay, yeah.
Yeah.
Okay then.
Okay then.
Okay. Yeah.
Thank you, everyone.
Thank you,
Okay,
Shairi.
thanks, Ritesh. Bye.
Thank you.
Theory, shall we close it? Okay, I'm ending the meeting for all. Thank you.